So our third exam, now on Monday, I'll hand out the exam I gave in the previous year. I want to have it before break because I have, meaning Thanksgiving, because if I have things after Thanksgiving, to be honest, they're a disaster. I mean, I have no problem doing that, but it's gonna, do you really want an exam Monday after you come back from Thanksgiving? I'm guessing probably not. That doesn't go well for anyone. So our exam will be the Monday before break. So our third exam, test 3, is Monday, November. We're up here, 25th. This is Monday before break. Okay, what is it going to cover? It's going to cover basically all the stuff on work and energy and all the stuff we're going to be doing this week as well, all the linear momentum and stuff like that. We'll probably finish up the linear momentum stuff certainly by next Friday, probably by Wednesday or so. Yes.
Do we have a final during finals week for this class?
Yeah, we do. Yeah, and it's wherever that it's specified when we have it. I don't make those
So
dates.
there's 2 dates for this class that.
No, there's actually one. If you look, there's one that says Physics 125, and that's the one we go with.
Okay, because
Okay.
there was one for like Monday, Wednesday, Thursday.
Yeah, so if you look though, there's an actual specific one, Physics 125.
Okay.
I don't make those dates when they are, just so you know, I don't come up with the final dates. But I do know whatever I've done, I've obviously, offended the final god because I always get really, really bad. You can pick up on. I always get kind of a bad home. I'm either right at the very beginning or usually right at the very end.
It's the
That
13th.
is that the first day or the last day or?
It's the last.
Yeah, sorry, I don't make those rules. That's just what happened. Okay. Okay, but here's this test here. So this test here is going to start with work energy. Okay. And it's going to go up to and including all the momentum stuff. Well, certainly finish it by Wednesday, probably even by Tuesday, because it's not. Once we get one more idea, we just do examples of it. It's just a matter of examples. Okay. That makes sense? This will be the hardest of the exams, other than the final, because one problem starts pulling in it. You're going to see that once we begin the momentum stuff, we can do one problem and it uses everything from the entire semester. Which either you love that idea or it just drives you nuts. I actually think it's beautiful. It shows you the nice thing you can do with physics. It's just once you get basic ideas, you can absolutely crush a whole number of problems that you just couldn't deal with before, which is really amazing. Okay, so with that said, let's go through and find the little thingy. Erase the board. I don't see the little thingy, which I don't mind as being my hand. Pulls out my wife does. But we'll do this. So Monday, November 25th, test 3. And who's invited? My people. My people are invited. So what did we have last time? So last time, we looked at basically, what did we start with? We started off with F net equals MA. And what did we do with that expression? We wrote A as dV dt. We took the dt over here. And then we integrated from 0 to t, so from v initial, some final v, which I'm just calling final v. This integral over here on the left, what do we call that integral? That is by definition it's j, which is we call the impulse. Okay, so we gave it the name j. Sometimes this is called I, but I'm going to call it j. I think that's probably a little more standard. This is the impulse. And then what happened over here? Well, if I integrate dV, I get V evaluated at V initial and V. So this gives MV minus MV initial. What do we call linear momentum? Linear momentum, we give the symbol P to it. And by definition, linear momentum P is mass times velocity. So this is what? This is going to be our P final minus P initial. And a final minus initial is called your change in P. And so what we had is that this J equals change in P. And what was that relationship called? The impulse momentum relation. So I mentioned something before. I said that once you kind of know basic physics, people think you can do, any type of problem that you come across. So people say, what is, if you're hit by a car, what force does that car exert on you? Sure, it's going to be actually, conceptually, it's actually very simple. Actually calculate it, this is another little thing. So let's do an application of this. So if you are hit by a car, what force does the car exert on you? Well, what kind of problem is this? It's exactly an impulse momentum relation. That's exactly what this problem is. So let's actually draw like a little picture here. So here's a car. It's going this way. And here you are. Okay. Now let's figure out where could this be complicated here? Let's just figure it out. So somebody comes up to you and says, you're hit by a car, what's the force? Apply that equation here. What's going to be the net force on this person for the most part?
The mass times velocity.
Or just in terms of words, what's causing the net force? Heck.
Oh, the car hitting.
Yeah, exactly. So when if you'd apply this here, if you'd have said this right here, we're going to apply this to the pedestrian. So what would this be? This would be from some 0 to t. This would be the force that the car exerts on you, dt. Okay. So this is the impulse here. And this is going to equal the final momentum of the pedestrian minus the initial momentum of the pedestrian. What is that little t called again? The contact time. Now we said that this force can be really, really complicated things. So what did we do last time? Give you a hint. We multiply the top and bottom here by t. And why did we do that? What do we know about this quantity right here? And that is the definition of the what kind of force? The average force. Okay. So what this gives us here, let's see, is this, let me get rid of the map. Here's the calendar. So what this gives me here is that the contact time times the average force that the car exerts on you. Okay, is equal to this P final minus P initials. So it's already one thing that's going to be hard to figure out. You'd have to estimate. Okay, you've watched enough movies, or maybe you've even seen a car accident in real life. What would be one thing you'd have to estimate with this? And it would be an estimation unless you can measure it. The contact time. So if you're hit by a car, how long is that car in contact for you? Like 3 seconds, 1/100, 2/100, 3/100. The 3 second spurt? Not really. I mean, how fast is a car if you're hit by a car? Pretty quick, pretty quick. Okay, so what might you say? 1/10 of a second? That to me seems a little still too long. Okay, maybe like 100th of a second, somewhere between 100th of a second and 1/10 of a second. But the point is that you have to estimate it. Okay, so you have to estimate the contact time. So the contact time must be estimated. Unless you could measure it. Maybe there's like a video camera. You could look at the frames between the individual frames of the shot, because it refreshes at some level. And so then you could actually calculate then the actual, you could get a better estimation for what delta T is. Unless you had a really fast optical camera. Okay, then what else would you have to do? You'd have to estimate.
Or the speed you're going initially.
Yeah, the initial speed here. So let's do an easy thing. What would be the easiest thing to assume for initial velocity? 0. Let's just say you're a pedestrian. You happen to stand in the crosswalk, and a car comes and runs you over. Okay, so let's just take this. Let's say v initial equals 0. So now I just get this p final here equals this guy here. Okay, which is going to be what? This is going to be some math. Let's go down. I'll go down here. It's going to be the mass of the pedestrian times the final velocity of the pedestrian. So what else would you have to do? We could actually measure the mass of the pedestrian. That'd be fine. Well, what else would you have to do? We need that final velocity. So what could you assume? Well, I mean, this is actually we're finding the force on this one. So it's not going to be it doesn't apply to the car here. This is going to be the final velocity of the pedestrian. So what could you do? You could say, well, I don't know what it is. Maybe you could put in the velocity of the car as an estimate. Let's say you get somebody is hit by a car. What do you notice about the pedestrian? Or maybe they're stuck to the windshield, in which case then the final velocity would be something comparable to the velocity of the car. Maybe they're kicked out like that, some velocity like that. So then in which case it's going to be greater than the velocity of the car. But you have to estimate this. So you'd have to estimate this as well. If you didn't have anything to measure up, so you'd have to estimate this. Okay. Then with these estimations, you could then come up with the average force that the car exerts to the person. But it's an estimation unless you have measurements. Okay? That makes sense? Now let's say you worked for let's say okay, who does the crash test in the government? Whoever does the crash test for the government. How do you then measure this? Or you could have meters, devices that actually measure force. But if not, what would you do? Well, again, this is where you would have that card is probably all filled up with sensors and who knows what. So you're probably getting actual real measurements for this, and then for this, and you know what you're hitting. So then you could actually calculate that. But again, probably what they actually do is have some sort of force probe like we had. They're probably actually getting what this force is as a function of time. But if somebody were to just ask you what's the average force that a car exerts on somebody if they're hit, that's a hard calculation. Okay, so the other one you get is what force is, I'm taking karate. What force do I need to hit a board with to break the board? Okay, that's a really hard question. I mean, conceptually it isn't until you go to work it out. So what force do you have to hit a board to break the thing? What do you have to apply? It's this exact same concept. Okay, so let's say here's a board. Let's say I have a sawhorse here. I have a board. And take my hand and I'm going to smash it. Okay. I actually had a good friend of mine actually does karate at a very high level, and he actually does that. He actually mentioned at one time he was doing demonstrations of this at the local high school. And his students couldn't break the board, which, that looks bad. And so he had to, and it turned out there was just a really, really nasty board. And he realized at the last minute that it was a really nasty board, but he had to have that board, break. And so he knew what was going to happen to his hand. He was going to break something, and he did. He broke the board, but he also broke a couple fingers. But if you knew the guy, this is just consistent with him. Let's just say he's a little more rugged than I am. So I was at, can't break, unbreakable. That would have been my response, but well, he broke it. Okay, so why would that be a hard problem to do? So if I had the board and I bring down my hand, what mass do I have? I mean, it gets rotten already there. Which part? Is it here? Is it a little bit here? I mean, just figuring out what part of the mass that's hitting it is really a pretty hard question. Okay, so you'd have some sort of estimation for whatever the mass of your hand would be. Okay, you could, if somebody were videotaping it, you could then measure the initial velocity, which you'd have to know. You could also then have to measure the final velocity here then as of your hand. Again, if that's videotaping, you could get it, but you have to estimate it. But what else is going to be the really, really hard? The contact time again. You can see if this contact time is small, but it's off of the forces here. The smaller that contact time, the greater the force. And so, and again, if you ever see these things broken or whatnot, they go lightning fast. When my friend would demonstrate karate moves, he would do them really, really slow so people could actually understand what to do. But periodically, he would actually show when if you're attacked, what would happen. And you don't even see anything happen. It's just all of a sudden the person's on the ground. Like, what the hell happened? And it's ridiculously fast. Okay, so these things are, I mean, and conceptually, they're easy enough questions to ask. And conceptually, you can do them, but in practice, if you want to go and estimate those things, it turns out to be really, really hard. Questions? Okay. So we have this expression here. And then what we did is we applied this to a system of particles. Well, let's just say to a system. Okay. And we applied that to a system. What did that equation come? So we applied this, the first mass, second mass, third mass. We added them all together. And what was our result of that? We calculated this J for the system. It turned out to be this integral from 0 to t of all the external forces on the system, dt, times a change in the momentum of the system. And what do we say if there are no external forces acting on that system? What could we then get? Yep. Conservation. We got conservation of linear momentum. So if the external forces on the system equals 0, your delta P of the system is 0. So that means that P initial of the system equals P final of the system. And this is our second conservation law, conservation of linear momentum. Okay, so we have two conservation laws. What are they and when are they valid? The first one we had is conservation of total mechanical energy, which is valid when no non-conserved work. And the last one is, second one is this, conservation of linear momentum, which is only valid when there are no external forces acting on the system. That makes sense? Questions? Yep.
If the external of the system is zero, if you take the derivative, then we still get a plus C.
Oh. If this is zero, right, the derivative of zero is not. Oh, you mean with the integral there?
Yeah.
Oh, so you mean if, okay, I see what you're saying. But if this is zero, that you get a plus C. Okay, so if that is zero, you get a plus C.
Is bounds.
There are bounds, but also another way to look at it is if you were to explain to a little kid what an integral is, what would you explain it? You have a little curve, what would you say? Area under the curve. So if I had my force versus time, there's no external forces is zero. What's the area under the curve? Zero. Okay. Make sense? Okay, so let's do a whole bunch of examples. Ultimately, we won't do it today, but okay, the actual name of this, I don't know what this is actually called. Newton's cradle. I call it the dumb executive game. Why is it the dumb executive game? Because if you're an executive, you have to have this on your desk. It's required, right? And then you have this. We'll be able to understand exactly how this works. So we're going to do something like this. Right? We'll figure out how this works. That's what we'll do. We'll start having it in class. And then we'll ask questions that match the rhythm of this. So if you ask we won't do that. No, that's irritating. Okay, so let's take an example here. Let's take this to be frictionless. Here's a mass. This is big M. We're going to have a gun here. Going to fire a bullet. This is M. This is V naught. And that bullet wedges right in here. The question is, for part A? What is the velocity of this block bullet system? Next week, we're going to do the ballistic pendulum, and the ballistic pendulum is going to be a variation on this. Does anyone know what a ballistic pendulum does? Let's say you have a revolver. What is the muzzle velocity of a revolver? It's the velocity of the bullet when it first comes out of the barrel. The question is, how would you find this? Well, the way you do it, until very recently, this device was always used. You actually use something called a ballistic pendulum. And that's what the lab will be. We'll do the ballistic pendulum. Not with a real revolver, but it turns out, I'll tell you an amusing story that one of my former colleagues before he retired, actually, when he did the lab, actually used a real revolver in the lab. And there's an amusing story with that, but that'll wait till Monday. Okay, so can you do the following? So let's say you see this on an exam, or you're an engineer and you have to do this, and you think, oh, I know what to do. Conservation of energy. So I'm going to say E initial equals E final. I'm going to say, is this correct? Now, obviously, by the way I'm saying this, the answer is no. Tell me why this is wrong. Why can't I say, oh, I know this energy here. It's all kinetic. Okay? And that's going to go into this energy here, and this is all kinetic too. So this energy here equals this energy here. Done. Easy question. Why is that utter nonsense?
If they're separated and then that after part of this is different volume because like.
Okay, when can I say this? The reason I keep on harping on when these laws are true. When can you say E initial equals E final? Yeah, so this is only no non-conservative work. This is only true. It's non-conservative work. So I've just drawn it like this, but if you're to have a bullet that embeds itself into a block, what would happen? Yeah, what are you that right? You're gonna basically have to put a hole here like this. The wood is gonna splinter in some really awful fashion like this. What's gonna happen? So basically the bullet's gonna break up all these wood molecules. You're gonna have friction on the side of the bullet here. Is that gonna be conservative work or non-conservative work? That's a whole lot of non-conservative work. And so there's a ton of non-conservative work going in here. So part of this kinetic energy goes into what? It goes into basically breaking up that wood. The bullet itself is going to be mangled a little bit. You're not going to have a nice twisting bullet afterwards. It's all going to be kind of messed up because basically they had to penetrate into that wood. So you have a ton of non-conservative work. My father, at some point when I was a boy, he had a 357 Magnum. And the Sears catalog came out, you don't know this, but you're too young for this. But the Sears catalog came out and it's always really, really thick. So my father basically wanted to see what this gun would do to the catalog, and it just completely shredded the thing. It was just shocking. Okay, it's really cool when you're like 8 or something. Oh, that's cool. Do it again, Dad. Okay, but kind of non-conservative. Okay, so what do you have to do now? The forces would be pathological. Why would the forces be pathological? What is the force that this block puts on this bullet? I have absolutely no clue. Hey, but is there another thing we could do? How come? When can I say this linear momentum equals this linear momentum? When the external forces equal 0. Now, are there any external forces? Again, this is my system. The system is this. This is our system. That's my system. There's an external force of gravity, but in the x direction. And the x direction, are there any external forces acting on this? No, there's going to be the force that the block puts on the bullet. But what is that? That's going to be an internal force. That doesn't matter. So when I look at this right here, I can actually say that I can say the external forces in the x direction equals 0. So what I can say is when I have this P of the system here like this. Initial equals P final of the system. Since there are no external forces in the x direction here, I can actually say that the x momentum of the system initially equals the final momentum in the x direction of the system. Does that make sense? So what is the initial x momentum of the system? They have to have the momentum of the bullet plus the momentum of the block. What is the linear momentum of this bullet initially? M times V naught. They'd have M times V naught. I'm going to put a 0 in here, even though it's kind of obvious it doesn't need to be here. That's going to be for this big mass here. Why is this going to be 0 here? Initially, it's at rest. So this is initially at rest. Okay, equals. Okay, so what is going to be then the linear momentum of this here? What is that bullet going to do? It's going to embed itself in this block. And after this embeds in the block, what do you know about the velocity of both of these? They're the same. So I can treat this as a unit. So what happens here is that this is going to be the mass of the whole unit, little m plus big M, then times that velocity, which I'm calling big V. What happens here? So, so for the big V by dividing through by that, the sum of the masses there, and I need this. Does that make sense? Hey, I think there's a part B. What is the non-conservative work done on the system? I hope there's a part C to this too. So pull it, beds itself in there. Okay, how much work is done by non-conservative forces?
So, shit.
Hey, is there an expression for that? I agree. And let's say maybe you had a test coming up. Let's call it, for lack of a better word, test 3. And let's say maybe you're all invited to test 3, and let's say this is on here. And this is part of the question. What crazy thing might you do? Is there a relationship for this? What do you know about the non-conservative work? It equals what?
Or
Change in E. So your non-conservative work equals E final minus E initial. Hey, do we know anything about the initial energy in the system? I mean, just energy in general. What is energy made up of? And kinetic. Okay, is there any potential energy on this in this problem? No.
not yes.
Okay, because we only have 2 types of potential energy. What are they?
Gravitational.
Gravitational. Do we have any gravitational potential energy? Not that changes, because nothing changes height. Okay. What is the other type? Spring. Are there any springs in this problem? Let's try again. Are there any springs in this problem?
Yeah.
No. Okay. So there is no potential energy for this. So the energies are all kinetic. So what is the kinetic energy, final kinetic energy of my friend here? What is kinetic energy always?
That's the sort.
1/2 mv squared. So what is the mass of the system here?
Yeah.
System,
Plus big.
little m plus big M. So this is going to become 1/2 little m plus big M. What is the final velocity of that system?
Big B.
That big V. Minus. Okay, what is the initial kinetic energy of the system?
The negative Q4.
I agree. Tell me what it is.
V squared.
The V naught squared, exactly. Do I know anything about big V? Yeah, it's up here. So I can put that in here. This is 1/2 little m plus big M times my big V squared. Minus my buddy over here. Let's clean that up. So our non-conservative work equals. So this gives me m squared v naught squared. This m plus big M comes in squared, but there's one up here, so it had then this just 1/2 here, little m plus big M minus this 1/2 m v naught. I could clean it up, but I'm just gonna leave it there. Does that make sense? Actually, I cleaned it up something. Okay, I can't leave it like that. I'm sorry, I have to clean it up. I factor out a 1/2 m v naught squared here. What would that leave over here? This would give me basically then the ratio of the masses minus 1. This is my initial energy, so my initial energy would basically differ by that fraction there. And I can't leave it like that either. Well, tell me what is screaming to be done. So, common denominator here. So common denominator here is going to be little m plus big M. So what happens here, the little m's cancel, I'm left with this. So I'm left with a minus sign here, which I pull out in front. Then just a ratio of those masses here. This shows me it's explicitly negative. Here's my initial energy here. And how much is this initial energy going to change? It's just the ratio of the mass of the block compared to the total mass of the system. Algebra is your friend. I hope there's a part C to this. If the surface has a use of K, coefficient of kinetic friction, what is the maximum distance the bullet block system travels? And gun, you fire a bullet, your mass M, there's now some use of K down here. The question is, what's that maximum distance? Well, there's a couple things we have to do here. There's some non-obvious points. How do you go about doing this? Now, this is starting to become a real problem now. I mean, in the sense of, I don't mean it kind of metaphorically. I mean, like, this is an actual real problem you might actually have to deal with. So, I mean, this is becoming a realistic problem. Once you have our energy and momentum in there, then you can start doing real things. Yeah, I'll call time. Okay, let's go through and break it up. There's kind of two parts to this. There's two parts. First part is this. We've already done it. We have this here. This is our before picture. And this is basically immediately after the collision. So now you see before and after pictures. This is part one. What do you think? Conservation law. And again, whenever you have a collision, do not think conservation of energy for the rest of your life. When you have a collision, the first thing you think of is conservation of linear momentum. Now you might yell out this and you could say, well, wait, when is linear momentum conserved? When no external forces. And you could say, the rule's been violated. How come? Yeah, it's acting in the X direction. So you could say, well, wait. When it starts moving, there's an external force, linear momentum is no longer conserved. Argue why I can do it this way. There's a very, very important word in this problem. Immediately. Okay. The word immediately is extremely important here. Why? Remember when we have this JX, J of the system. We have this here. What's going to happen here? How long does this take to occur? Almost instantaneous. So what's the T going to be?
Varies.
Effectively zero. Okay. So what does that mean here? That means here that I can say this P initial equals P final as long as you do it immediately after. Okay. So I can say P initial X of the system equals P final X of the system. And this, we did this before. And now this gives me the big V is equal to little mv naught over little m plus beta. That's part one, just what we had before. Now, what is part two? Okay, that's not a concept. Give me a concept.
Did we take like the little distances?
You could, but you could be even faster with this. Let me draw the picture here. So this is part two of the problem. So this is immediately after the clipping. What does that smell like? Well, free-body diagram. More? I could do this with an F-nat. Now tell me why I'm not going to. There's nothing wrong with doing that. I could do it with an F-nat and that'll work. But since we're getting ready for test 3, let's do it with our brand new shining methods. What's our brand new shining method I could use for this? Conservation. When is energy conserved? When there's no non-conservative work. Is there non-conservative work here? Yes. So tinker with what you said. Go back one step. Think about where conservation of energy came from. Okay. So, 4.5 step, okay? The non-conservative work equals, I mean, that will work. It's going to be just a little bit easier if you do this one. So what is the non-conservative work being done in this object here? Immediately after the collision. Where? Only on this part here. Why don't I have to worry about all the non-conservative work for that bullet burying itself in that block? That was all done. That was basically done, immediately after the collision. That's already been done. So that no longer, that's in the past. We don't have to worry about that part of it. So we have here, it's just non-conservative work of this object sliding along here. So this is going to be minus the kinetic frictional force times its X max equals E final minus the initial. What is your kinetic friction given by? Minus mu sub K times the normal. What's the normal force in this case? Little m plus big M times G. This right here is my normal force. Times your X max. What is your final energy here? Because at the X max, what does it mean? It means that this thing has stopped. This, right, if this isn't at the max, if this is still moving, it's going to continue to go, and you're not at the X max yet. So at X max, this has to be 0. So this has to be 0 minus, what is your initial kinetic energy? One half? Which mass? Little m plus big M here times your big V squared here like that. And that term cancels this term. What happens to these alpha minus signs? They cancel. That's always very nice when our minus signs cancel. So this gives me X max equals this big V squared over 2 mu sub K G. This is just my little m V naught, little m big M squared over 2 mu sub K G. So if I wanted to, I could actually use this as a method then to calculate or to measure mu sub K. What I could do is I could take the mu sub K over here, the X max here. I have my little block on the table. I take my little revolver, I fire it into that. What I can do is then by measuring my X max, I can then measure the mu sub K. Pretty slow. Questions?
Is it safe to say that that's gonna be that?
My cats love physics problems where you have to use 2 or 3 parts to them. Speaking of that, let's look at something that was set up and then we'll go on. We'll solve it explicitly on Monday. My cats love these projects. Let's take another example. A gun. Fires a bullet. We're going to have a lot of guns firing bullets here. Into a pendulum like this. Like this. Okay. This is at rest. This is going to swing way up here. I want you to find the tension in the string at that top. Okay. That's a beautiful problem. And it's actually, now you know exactly how to solve it. My cats love problems like this. Okay, how do you have to do it? I'll give you a hint, there are 3 steps. And they have to be followed in this order. Well, the first has to be done first, which is why I said first. Yeah, break it up. So the first step is conservation of linear momentum, where and where?
Initially with bullets fired
And, okay, that's the initial.
when it hits the block.
Put in more words there. You're not wrong, I just want a more detailed answer. Immediately. Yeah, immediately after the collision. Immediately after the collision, where's the block bullet system?
Together.
It's still down here. That's the first step. What's the next step?
Circular motion.
Circular motion is coming in. Why do you know circular motion problems coming in?
Because it's going in the circle.
Correct. Okay, and what am I asking for?
Tension.
attention, that's the force word. So that is there. I'd make that actually the third step.
Okay.
Although you could do it the second. How'd you go from here to here? Immediately after the collision, right, all the non-conservative work's been done. Is there any non-conservative work going from here to here? No, therefore you would have,
Conservation.
there would be an external force, gravity. You'd have conservation of energy. So it's a three-step problem. You have conservation of linear momentum just before and just after the collision, conservation of energy immediately after the collision to get you up here, and then a circular motion problem to can then get potential. So notice our little problem. Remember this little course, how it started off so simple? You know, a block moves this distance. What is the average velocity? It doesn't end this way. It ends actually with a very, very sophisticated calculation. Okay, we'll do this on Monday. Have a good weekend.